Okay, guys, so now we are moving on to section 6.4. And in section 6.4, we are going to be studying how we can use confidence intervals to estimate for a population mean if we don't know it. And so in this case, think about what we take means of, right? Speeds, weights, heights, time, things like that, grades or scores even. So it's a little different context for these problems, but very, very similar process. The steps are identical, right? And so those three conditions stay the same. We still have to take a random sample. Our trials still need to be, or our samples still need to be independent, meaning that N, our sample size, is less than 10% of the population. Alrighty. And then last but not least, this one should make us happy. To prove that they are normal, because this is for means, all we have to show is that N is greater than or equal to 30. Right? And we learned that last unit. The only exception to that was if we knew it came from a normal distribution. But remember, we don't know what our population is, so we won't know that our population is normal. So we're always going to have to show that N, our sample size, is greater than or equal to 30. Now that general framework stays the same. This is the same as the one that is on your formula sheet. But in this case, because we're using sample means to estimate for population means, we start with a statistic X bar, plus or minus. Now this is the big difference. This is like the one big difference other than the formulas. Our critical value here is called a t-score. I'm going to talk about that in a second, but that's a big difference. And then the standard error or the standard deviation is Sx, our sample standard deviation, divided by the square root of n. So if we look back at our formula sheet, here we're down here, sampling distributions for means. We've got one population, and it's just S. I use Sx, I guess, because that's what the calculator says, but it's just S, your sample standard deviation, over the square root of n. All right, so we could even get rid of that x if we want to. So let's talk about the t-distribution. So the t-distribution is one we use only when we calculate a confidence interval, or next unit when we run a test of significance for a population mean. So that's really important. We only use it for means. And because, we use it because we don't have the population standard deviation. So this is just one of those weird rules statistically that we have to follow, specifically because we do not have all the information that we need in order to use the z-score. So when we use a t-distribution, we use what are called degrees of freedom. Your degrees of freedom are always equal to n minus 1. So whatever your sample size is, minus 1 from that. All right, so now let's talk about where we find this. The t-distribution is located with your normal distributions, with your all that. Where normal CDF is, that's where you're going to find this. And so if you hit on your calculator second vars, you're going to look for inverse t. On my calculator, it's 4 in that menu, so hopefully it is for yours as well. Now when you hit enter, it wants the area. For all my friends who are used to using that center area for inverse norm when we calculated percents, this is different. This is always the area to the left. So that you're going to have to remember to do that a little differently here. And then, of course, we just said degrees of freedom are equal to n minus 1. Okay, so let's practice this. If we are finding a t-score for a 90% confidence interval, where n is equal to 100, we still draw a bell curve because a t-distribution looks just like a normal distribution. It's just a little bit different. We know we have negative t and positive t with 0.90 in the middle. If 90% is in the middle, then 10% is outside, which means 5% is on either side. So 0.05 on either side. So we're going to plug in our calculator, inverse t, 0.05, that's our area to the left, with 99 degrees of freedom, because that's how much is left when we subtract n by 1. So 0.05, 99. Enter, and I get plus or minus 1.6603, so 1.66. All right, so I'm just going to carbon copy this, paste it 2 more times because we're just going to repeat the process to practice. Okay, so in this second example, we are doing a 96% confidence interval. Sorry, I'll clear all this out for us first. Okay, so 0.96 is in the center, which means 4% is on the outside. Split up, we've got 2 and 2, so our area here will be 0.02 with, not 11, 9 degrees of freedom, 10 minus 1. And I get plus or minus 2.398, so I'm going to say 40. And then here we've got 98% in the middle, so 1% and 1%. All right, so inverse T, 0.01 is our area to the left. And if we've got n equals 26, we have 25 degrees of freedom. Okay, so this is plus or minus 2.485, so 49. Okay, so that's our new critical value. So means we use t-scores, percents we use z-scores. Means, t-scores, percents, z-scores. So now let's calculate our first confidence interval. Okay, this says you want to measure the average number of calories in all of the chocolate milkshakes made at Steak and Shake. In order to do this, you buy one every day for a year, ensuring that your sample is random by drawing a time and location from a hat, and you measure the caloric content each day. You find that the mean number of calories in your sample is 500, and the standard deviation for your sample is 10.2. Calculate a 90% confidence interval for the average number of calories in all chocolate milkshakes from Steak and Shake. So here we are estimating the mean number of calories in all chocolate milkshakes from Steak and Shake. All right, we're going to do so using a 90% confidence interval. So our confidence level is 90%. Okay, now we check off our random. It says you ensured random by drawing a time and location from a hat. So yes, it's random, independent. Well, remember, independent, we need our sample size. In this case, 365 days in a year. That's definitely, less than 10% of all milkshakes. And then normal. This one is normal. Remember, t-distribution is basically normal distribution. That's why we require it. And so, yes, it's normal because 365, our n value, is greater than or equal to 30. All right, so now we do our calculations. And so our calculations start with x bar. Remember our formula from up here. I can copy and paste it so that you've got it for a reference. Says we start with our sample mean. Our sample mean was 500 plus or minus. Now we have to do inverse t. I'll just write this up here. 90%. Okay, so 0.05 and 0.05 are on either side. So, whoops, we would put in inverse t 0.05 and 364 degrees of freedom. And I get plus or minus 1.649 times that standard deviation over the square root of n. Okay, so now we're going to do 10.2 divided by the square root of 365. Multiply that by 1.65. There's our margin of error, 0.8809. Okay, that's a tiny margin of error. Let's think about why that would be, right? What is really, really large in this sample compared to other samples or other examples we've done? N, right? We took a pretty darn large sample size. So that really, really, really decreased our standard deviation, which in turn really decreases the margin of error and will create a very small confidence interval. So when we do 500 minus 0.8809, we get 499.119. So we'll say maybe 1, 2. Then if we add, obviously we get 500.88. Okay, now we interpret. We are 90% confident that the population mean is between 499.12 and 588 calories. All right. So we basically have zeroed in this case, on how many calories are in each milkshake. And most of that is to do with how large our sample is, right? And so just remember, if you added or increased on your confidence level, so if we chose to do a 95 or a 99% confidence interval instead of 90, that would have increased our interval size a little bit, but not by as much as you might think. So in general, having such a large sample size really helped make sure that confidence interval was small. All right, so today we talked about t-distributions, t-scores in order to calculate confidence intervals for means. You have 2 examples, so I hope we get those done, and I hope you all are doing well.